All right, the plan for today is to finish up the section on continuity 2.5 and work through section 2.6. We should get through most of it, hopefully all of it. But if we have a couple problems left over, we might knock those out next time. And that's on limits at infinity in horizontal asymptotes. And then the plan for Wednesday is to cover section 2.7 and start section 2.8, introducing this idea of derivatives, one of the big ideas in calculus, and pretty much where we're going to spend most of the rest of our time in Calc 1. We talk a little bit about integrals at the end of the course, but most of the rest of Calc 1 is going to be focusing on derivatives and applications, theorems related to them, and so on. The quote of the day today is from chess grandmaster Daniel Naroditsky. And it's, I guess, a little less of a quote and a little more of kind of an idea that comes up often in his YouTube videos and streams and things, where he talks about the difference between abstract and concrete advantages, and particularly the idea that if you have an abstract advantage, it can kind of disappear unless you do something to turn it into a more concrete advantage. So in chess, that kind of, that often looks like something like maybe a development advantage where a lot of the difficulty of chess in the early stages of the game is getting your pieces out from behind your pawns so that you can use them to control squares and to attack and so on. So maybe if you have, three minor pieces out and your opponent only has one piece out, you have an advantage at this point. But if you don't push that advantage forward, if you sit back for a couple of moves, your opponent gets a couple extra minor pieces out, and then you're even. That advantage has disappeared. Versus, say, a concrete advantage, if you can turn your extra piece development into an attack, maybe you have a little more weaponry out than your opponent has to defend. Maybe you can win one of their pieces and they're without that piece for the rest of the game. That's a much more concrete advantage. And I think this, like a lot of chess principles, applies more broadly than just in the game of chess. A couple of places that I think this applies fairly directly to this course and to your kind of time here at CCAC is most of you are planning to get a degree, move into a career field. It's maybe a career that you think that you'll enjoy doing, that you'll find purpose doing, that you think will give you a good, family supporting salary, and you'll be able to enjoy that career for all those reasons and more, hopefully. But the degree is kind of the first step to that, right? If you get a degree in a field, that doesn't get you all of those things. The degree is in some sense kind of an abstract advantage, and if it just sits there on your shelf and you don't do anything with it, it just goes to waste. It's not going to create that sense of purpose or that income for you. You have to take that degree and parlay that into something more concrete, like a job, a career, something purposeful, etc. Or maybe more locally in time to this class, especially in remote classes and especially in online classes. There's, it can be a little bit hard to keep up with the pace of the course or to kind of do that time management aspect of things for whatever reason. Whenever we kind of physically go to the campus and, we're sitting in a seat, for some reason, it's just a little bit different psychologically than if you're watching, watching my lectures over Zoom. And maybe that means that at the beginning of each week, you sit down, you make a study plan for that week. These days, these times, I'm going to study calculus, or I'm going to work on chemistry, or, practice my speech, or whatever it may be for another course. And that's great. That's an abstract advantage. The fact you've taken the time to sit down, spend 10 minutes, look over what you need to do this week, plan out some schedule. But if you don't actually prosecute that advantage, if you don't move forward with that, it doesn't turn into anything concrete. If you play video games or go hang out with friends or sleep in instead of doing the stuff that you had planned to do, that advantage disappears. It doesn't materialize. On the other hand, if you do move forward with that plan, even if not perfectly, if you, do it most of the way, then that turns into something more concrete, better grades on homeworks or papers or something like that, better exam grades, maybe better course grades, and or maybe something like, say, less stress around exam time or when there's a big project due. So it turns into something more concrete that's more lasting. And I think that this idea applies in a lot of other places as well, but that's maybe two that more directly apply to your academic experience here. All right, so moving into the material for today. Any questions on anything before we move into 2.5 and continue on? Okay, so recall from last time, we introduced the idea of continuity and we said f is continuous at A. Essentially, if this kind of plug-in property of the limits that we really were tempted to do, but we saw we should be a little careful with that, if that works. So if that plug-in property works, then we say the function is continuous at that point. Recall that this is really three statements, that f of A exists, that the limit exists, and that the two are equal. We discussed the extreme value theorem that continuous functions on compact sets or on the real line on closed and bounded intervals achieve their extrema, they achieve their maxima and minima. There's an input that yields an output, which is the maximum output, and similarly for the minimum. And we had a couple of theorems that if I have two functions, f and g, that are continuous at a point, then combinations of those functions are also continuous at that point. That means if I take those two functions and if I add them, subtract them, or multiply them, the resulting function is continuous. And if I divide them, so long as I don't introduce a division by 0, still continuous. And we had another theorem that said all of these classes of functions on their natural domains are continuous. Polynomials, rational expressions, we've seen those two already in a previous section, but also radicals, trig functions, inverse trig functions, exponentials, and logs. So lots of continuous functions. In fact, probably most of the functions that you could think to write down in any kind of reasonable way, we would call continuous functions on their domains. Okay, so a couple of new theorems that we're going to use, and then we're going to work through some examples. So one thing that we did not handle in this case, combinations of functions don't include compositions of functions. So can I share my whiteboard? I thought that my screen was being shared. Is anybody else not able to see my screen that I'm on right now?
I can see it.
Okay. Yeah, so my screen should be shared. Are you seeing, if you're seeing just my face, you might have me like pinned. Sometimes on what is it, on the top right with the like three little dots, sometimes you can like pin somebody. So if you have me pinned, maybe try to unpin me. So did that fix your, are you able to see the whiteboard now? Let me try exiting out of the share and just restarting it and see if that will help. Here, I'll just restart the share. We'll see if that fixes it. Okay. Okay, yeah, if that doesn't fix it, yeah, maybe try restart Zoom. As you said, I did redo the share, so hopefully that helped. If that didn't help, maybe try restarting Zoom. And if you're still not able to see it, then definitely let me know. Okay. Okay. So one thing that we did not handle in this theorem are compositions of function. That's super important. So for instance, we have a trig function like sine x, and we have a polynomial like say x squared. Well, x squared times sine of x is continuous. Those functions, s squared and sine of x, are both continuous in the real line. Combination like say x squared times sine of x or x squared plus sine of x, continuous on the whole real line as well. But what about something like sine of x squared? Or what about something like sine of x all squared? Well, I mean, I guess sine of x all squared, we could kind of manipulate to be sine x times sine x. So maybe we could still handle that here, but something like sine of x squared, that's a little harder to manipulate, right? It's kind of somehow more inherently a composition of functions. So if I have a composition of, say, a trig function and plugging a polynomial into it, is that continuous? So we have a couple of theorems related to that idea. When we're plugging one function into another, we have composition of functions. We have to treat that as kind of more of a special case. So our first theorem, if f is continuous at a point B, and if limit x goes to a g of x equals b, if that limit exists and equals b, then we can say the following. Limit x goes to a f of g of x equals f of limit x goes to a g of x equals f of b. Because this bit here, by assumption, was just b. So what does this mean? This means that, in a sense, kind of limits can pass through continuous functions. So because f is a continuous function, at least at where it will end up being evaluated at, the limit can pass from the outside of f through to the inside of f and kind of hit g directly, and then we can use this assumption. So kind of more generally, we think of continuous functions as having the property that the limit can come inside, can pass through the function. We actually might even come up here and realize that that's kind of a way we can interpret this definition. We could think limit x goes to af of x. Well, if f is continuous at a, if I have a continuous function and I can move the limit inside, right? So we can even think of our definition as basically being this criterion, that we can pass the limit inside of the function from outside to inside. So that's an important idea in continuous functions. Limits can kind of, in a sense, move inside of continuous functions. And then we have a slightly more general theorem. If g is continuous at a, and if f is continuous at g of a, we have to be careful here, because when we have a composition like f of g of x, I have a domain for g and a range for g. So g takes inputs and converts them to outputs. And the outputs of g are actually what's being plugged into f. So something like the range of g has to mesh with the domain of f for compositions to kind of work out nicely. So if g is continuous at a, and if f is continuous at g of a, what will end up being plugged into f, the output of g, then their composition is continuous at a. That is to say that the limit x goes to f of g of x, we can do the plug-in property for the entire function f of g of x, turning it into f of g of a. Or again, another way you can think of it is, well, f is continuous, so the limit can pop inside. Limit x goes to a g of x, but g is also continuous. That's just g of a. So these two theorems say pretty similar things, but note the difference that up here, the limit only needed to exist for g, whereas down here, we're actually plugging a into g, right? I mean, we could have a funky g where, g of a doesn't even exist, and this could still be true, because nowhere are we saying anything about g of a, but here we're saying g of a. So a little bit of a nuance between these two theorems, but they're saying fairly similar qualitative things, that limits can move inside of continuous functions. Now, for an example here, let's consider this question: is the function 1 over sine x continuous on open 0 to infinity? And this is a little bit of a trick question, because we might reason like this. We might suppose something like yes, because, well, let's say that this is, let's call it h of x, 1 over sine of x. And it's kind of like plugging sine x into 1 over x. So it's kind of like having f of x is 1 over x, and g of x is sine x. So h of x is the composition f of g of x. And I might look at this and say, well, f is continuous, 1 over x is continuous on open 0 to infinity, and g is continuous on open 0 to infinity. So these are both continuous functions, f and g, therefore their composition is continuous, and this is a continuous function. Does it seem right? Do you see any problems with this or any thoughts? Can you come up with a counterexample just to argue that this ought not be the case? Is there an input that you can think of on open 0 to infinity that would just, blow this whole claim out of the water? Well, what about h of pi? Well, that's 1 over sine pi, but sine pi is 0. So what happened here? What did we do wrong? I mean, this seems like a pretty reasonable argument. I think, I think most folks who have just read through the continuity section would see this argument. They'd say, yeah, sounds good to me. It's a continuous function. But really easy nuance to miss is g is continuous at a, but f is continuous not at a. That's not the criterion, but at g of a. Right? G kind of transforms the inputs, the kind of domain, so to speak, into some other interval. So is G continuous at A? These are like the A's. Yeah, there's nothing wrong with that. Sine x is continuous on open 0 to infinity. And it is a true statement that f of x is continuous on open 0 to infinity. That's not that's not an incorrect statement. But it's a statement we don't care about. It's not this criterion. So while this is a correct statement, it's not the statement we care about. We care about, is it continuous on, well, if I plug 0 to infinity into G, what do I get as outputs? Minus 1 to 1. Is it continuous on closed? Minus 1 to 1. The outputs of G when I plug in inputs in this interval. And now we see the problem. G maps most intervals, a big enough interval, to the closed interval minus 1 to 1. And f is not, maybe I'll even write it in red, f is not continuous on closed minus 1 to 1 because clearly 0 is in there. And that's our problem. So actually, no, this function is not continuous on open 0 to infinity. Again, pretty tricky once we get into compositions of functions because we need to be thinking of the inside function cares very much about the interval that we initially say, but the outside function doesn't really care about that interval. It cares what that interval gets mapped to by the inside function. The inside function g maps 0 infinity to minus 1, 1, and that breaks f, so to speak. So no, we can't just apply this theorem here because f is not continuous on closed minus 1, 1, the important interval of consideration because it's the outer function. It's having the outputs of g plugged into it. Any questions on that? Is Mark, did restarting Zoom or me restarting the share, did that fix the problem you were having?
Yeah, I'm fixed here.
Okay, all right, good. Just wanted to check. Okay, so moving on to our next theorem. This is a really important theorem for I think several reasons. One, this structure of theorem we see several times throughout the calculus sequence. So this kind of just general framework is a common one that we'll see a few times. Also, it leads to some very practical results that might not be immediately apparent from just looking at the theorem. Okay, so the theorem is called the intermediate value theorem. We're not going to provide a proof of this. there's a proof in the book, I believe. So I'll refer you to the book for the proof. But this is the intermediate value theorem. Suppose that we have a continuous function on closed AB, and that f of a is not equal to f of b. Let n be a number between f of a and f of b. Since we don't know whether f of a is the bigger output or the smaller output, we'll just say it this way, a number between f of a and f of b, meaning strictly between. Then there exists C in AB, in open AB, such that, missed the piece here when I was typing this out, such that f of c equals n. Okay, so what is this theorem saying? It's saying, suppose we have an interval a to b, thinking of a closed and bounded interval. I have some function that's continuous, so I can draw it from a f of a to b f of b without picking up my pen. I have that f of a and f of b are not equal. Let me edit my function here really quick. I want to make this a little easier for me to draw. Just a little more separation between f of a and f of b. So f of a is not equal to f of b. And then what we're saying is, suppose we pick a number n that's between f of a and f of b. We're claiming that there exists C in open AB such that f of c equals n. Or in other words, what I'm saying is that if I kind of follow n across horizontally, I can find an input that yields that output. So for instance, for this C that's between A and B, f of c equals n. Now, a couple important notes here. First, the theorem claims existence, not uniqueness. So it's not saying there's exactly one such C. It's saying there's at least one such C. In other words, that it's not true that there's no such C. So I could have chosen this one. We'll maybe call this one C1. Or I could have chosen this one or this one. These would all be C's that kind of satisfy this criterion for this choice of n. A different choice of n, say up here, we could come out with a case where we have only one value of C, only one input that yields the proper output. But we can never, under these assumptions, find an n where there is no C such that f of c equals n. There's always going to be at least one. There might be exactly one, there might be two, there might be 12, but there's at least one. Note that the closed interval is actually pretty important here. If we had a continuous function on, say, the open interval, we could actually find a pretty simple counterexample. We could take a function that is just, say, constant on that open interval, and something like this, right? So that this is f of a, this is f of b, and if I pick n between the two, it doesn't cut the function horizontally anywhere. I've basically jumped over n. I mean, pretty clearly, if we get rid of continuity altogether, right? If we forgot about continuity altogether, the problem is that I could just jump over the desired value, the desired output. But even if I keep continuity, but just on the open interval, I can go out to the very edge and then jump. So I do need continuity. I think it's pretty obvious why we need continuities, because otherwise we can just jump anywhere that we want. But we actually need continuity on this closed interval, this compact set, to make this all work out. Okay, so we have two examples here, two questions. Um, the first one is maybe a little more abstract, and we'll see something maybe a little more applied in the second one. So the first question, is there a number that's exactly one more than its cube? Maybe I'm solving a problem, and the crux of the problem essentially turns out to be, is there a solution to this equation or not? This happens in some applied problems where you want specific criteria so that, say, no solution exists. This one application of this is in mathematical finance. For the no arbitrage condition, you want your linear system to be set up in such a way that essentially there's no way to make free money out of the market, because we presume that if somebody could make free money out of the market, they would do that a whole bunch, and then all that free money would go away. So there are even practical applications of fairly abstract sounding questions like this. Okay, so a number exactly one more than its cube, is there an x that's exactly one more than its cube? Now I can kind of answer this qualitatively. I can say, my guess is yes, because I know that cubics basically look like this, right? Maybe some variation of this shifted left or right. It might have, you know, more of a peak and trough kind of a deal, but I know that that if I'm looking for a root to x cubed minus x plus 1 equals 0, or if I'm looking for a root to x cubed minus x plus 1, or if I'm looking for a solution to this equation, then I got to have one, right? I might have one, might have two, might have three, but basic kind of geometry tells me that I've got to have one. But can I actually prove this carefully? Well, one thing that I know is I know that f of x equals x cubed minus x plus 1 is continuous on the whole real line R. It's a polynomial, its natural domain is the whole real line, and we have a theorem that says polynomials are one of those, one of the members of those classes of continuous functions. So that means whatever closed interval I pick on the real line R, f will be continuous in that closed interval. If I can find a closed interval AB such that f of A, for instance, is less than 0, and f of B, for instance, is strictly bigger than 0, or vice versa, f of A could be bigger than 0, f of B less than 0, well, then what do I have? I have a continuous function on this interval AB such that f of A is not equal to f of B, and I have obviously that 0 is between those two, because one is negative and one is positive. In other words, I have a continuous function that between A and B must cross the x-axis, so it has to have a 0 somewhere in between there. So now my problem is finding section A and B. Well, let me start with f of 0. That's a pretty easy one to plug in. F of 0 is 1, which is bigger than 0. And now my question is, can I find an input that yields a negative output? Well, I mean, just by knowing a little bit about algebra, I know that cubes grow faster than linears. So if I pick a bigger negative number, I should get a negative output. If I pick something like maybe -2 is the input, -2 cubed is -8, minus a -2 is +2 plus 1, -5, which is less than 0. And now I see that I have an interval -2 to 0, a function that's continuous on that interval, -2 to 0, closed, -2 to 0. F of -2 is negative, that's a negative output, and f of 0 is positive, that's a positive output. So they're clearly not the same number, and 0 is between them. 0 is between, I'll just say, between these. So my intermediate value theorem implies there is a C, and I actually get a little more. I get a location of such a C. There's a C in the interval -2 to 0 open, such that f of C equals 0, or such that that number C is exactly one more than its cube. I don't know what the number C is. I guess have a region where it could exist, but I know that such a C exists. Now, something important to note is kind of a side note. Maybe I did, f of 1 equals, maybe I searched here, I was curious. I got 1 cubed plus 1 is 2 minus 1 is 1. Well, that's also bigger than 0. Very important to apply the right logic here. It is not true. Maybe I shouldn't write it in green if it's not true, but I've already used red. It's not true to say there's no root between 0 and 1. This is not the correct conclusion. Remember that intermediate value theorem is an existence theorem. It's only one directional, though. I could very well have a function that does something like this, right? Just because the 2 points I happen to look at both happen to be positive doesn't mean that it could not have gone negative, or not have that it could not have crossed 0 somewhere between them. So the converse of the intermediate value theorem is not in general true. We have to be very careful which way we use theorems. We'll do a little primer on logic at the end of section 2.8, beginning of chapter 3. But we do want to be careful about these things. So it would not be true for me to say I tried f of 1 and it also was positive, so there's no solution between 0 and 1. However, if I try f of 1 and it's the same sign as f of 0, that's simply just unhelpful for me. There might be a solution between them, there might not be, but it doesn't help me answer this question. So it's just not a very useful number to plug in or a useful output to look at in this context. It doesn't really say anything one way or the other. But by looking at, say, an input of -2, that does clarify things. So they get one negative output, one positive output. There's got to be an input between those two inputs that yields a 0 output. Okay, let's look at an example that's maybe a little more practical. We want to find a root of x to the fourth plus x minus 3 to 1 decimal place of accuracy. And as a hint here, we're going to consider the interval 1 to 2. So we'll name this f. And we see that f of 1 is 1 plus 1 is 2 minus 3 is -1 is less than 0. And f of 2 is 16, 18, minus 3 is 15, which is bigger than 0. So we know that there's a solution on the interval 1 to 2. There might be one solution on that interval, there might be 20 solutions. We're just trying to find a root. If I said something like find all roots on this interval, intermediate value theorem isn't going to be super helpful there. But we're just trying to find a root, so if I find whatever root, I'm happy. Now, okay, so I have an input of 1 and an input of 2. My input of 1 yielded an output that was negative, and my input of 2 yielded an output that was positive. I know that f is continuous, of course, right? I don't think I explicitly said that, but it's a polynomial. It's continuous. It's got to cross somewhere. It might cross like that. It might cross over here, or it might cross, a couple times. I'm not sure, but I know it crosses at least once. I know there's at least one input that yields an output of 0. Now, what I could do is I could investigate and uh, another point in the middle. I was going to say an intermediate point, but I don't want to. It's not the intermediate value theorem for that reason. It's intermediate in the outputs, not the inputs. I could use I could investigate an input in the middle here, maybe something like 1.5. Now, one of three cases, I suppose, will happen. I mean, I guess one case is I plug in 1.5, I get an output of exactly 0, and there's your answer. Let's presume that's not going to happen. If that doesn't happen, 1.5 is either going to have an output that is a positive number or a negative number. Maybe you can see what we're going to do now. If 1.5 has an output that's positive, then I don't know what happens on 1.5 to 2, but I know that there has to be at least one solution on 1 to 1.5 because I've switched from a negative output to a positive output over that interval. I'm going to forget about 1.5 to 2. There might be another solution over there. I don't know, but I'm going to forget about it and just concentrate on 1 to 1.5. On the other hand, if the output of 1.5 is a negative number, again, I don't know what happens on 1 to 1.5. Those two inputs have the same sign as the output, but I do know that I switch sign on my output between 1.5 and 2. There's got to be at least one solution over there. I want to forget about 1 to 1.5 and constrain my search to the interval 1.5 to 2. And then I'll do it again. I'll pick, maybe 1.75, see where I get a sign change, constrain my interval, pick the midpoint of that interval, see where I get a sign change, constrain my interval further, and so on. And this is called the bisection method. Because each time that we do an iteration of this, we bisect the interval. We cut the interval in half, and we cut our potential error in estimating this root by half as well. Right? If I told you that the root is somewhere in the interval 1 to 2, your best guess might be 1.5. Right? It's kind of the right in the middle there. It's going to have the lowest maximum possible error. If I told you it's between 1.5 and 2, your guess is going to be 1.75 with the maximum possible error of around 0.25. So our interval width gets cut in half each time, our maximum error gets cut in half each time. And that's the bisection method. So a direct result of the intermediate value theorem. So let's actually investigate this function. So we have our input and output. And I think I'm actually going to try to color code these a little better. Maybe I'll make the green positive and red negative. So when I have an input of 1 or 2, I don't actually care what the number of my output is. I just care whether it's positive or negative. So 2 gives me a positive output and 1 gives me a negative output. And now I want to investigate 1.5. I know that a solution, at least one, lives on the interval 1 to 2. Let's check 1.5, see whether it's positive or negative. Where can we get a sign change? So give me a second to bring up the calculator and swap my screen share around. Okay, so you should now see my my whole screen with the calculator on it. Yeah, looking good. And on the calculator, I'm going to go into my y equals menu. I'm going to put in this function so I can evaluate it pretty quickly on the table. So x to the fourth plus x minus 3. I'll go to table start and I'll do 1.5. So second window is table setup. And then second graph gives me the table, just lets me evaluate the function. There are some slicker ways to evaluate functions, but I think this is actually probably the easiest way. So this gives me an output 3.56 or so, but importantly, it's a positive output. I don't really care what number it is. I just care that the output is positive. So we're not in this situation. We are in that situation. There might be a solution on the interval 1.5 to 2. I don't know. But I know for sure there's one on 1 to 1.5. That's guaranteed by the intermediate value theorem. Let me forget about 2. And now I'm just concentrating on the interval 1 to 1.5. At this point, my solution can be anywhere between 1 and 1.5. I haven't gotten one decimal place of accuracy yet. So let me go to maybe 1.3. I could go to 1.25, but trying to keep it a little bit easy here because we only need one decimal place of accuracy. So if I go to 1.3 as the input, my output 1.15, still a positive number. So for say 1.3, still a positive number. Between 1.3 and 1.5, again, there could be a solution there. I don't know, but I can't guarantee it. The intermediate value theorem, though, does guarantee a solution on 1 to 1.3. So I'm going to forget about the 1.5 now and just concentrate on 1.3. All right, maybe if I go down to 1.1, see what I get there. Go to table setup, plug in 1.1. Well, here I get an output of negative 0.43. Not super interested in the number, but I'm interested in the fact that it's negative. 1.1 gives me an output that's negative. So here is 1.1 with my negative output there. Again, might be a solution on the interval 1 to 1.1. I don't know. But I know for sure there's one on the interval 1.1 to 1.3. What about 1.2? That gives me an output of 0.27, a positive number. 1.2 gives me a positive output. Again, 1.2 to 1.3, I threw out 1. I'm looking on 1.1 to 1.3. And then 1.2 to 1.3 does not give me a sign change, but 1.1 to 1.2 does. So between the two inputs, 1.1 and 1.2, my outputs switch from negative to positive, meaning that somewhere in that interval of inputs, 1.1 to 1.2, there has to be an input where f of x equals 0, there has to be a root. So there has to be a root on 1.1 to 1.2, or the root is 1.1 something. So I know the first decimal place of my solution. It's 1.1 something. So the bisection method, each step that we do cuts our error by half. So if I do 10 steps, it's like 1 over 2 to the 10th, about one out of 1 out of 1,000 or so, then my error gets cut by. So 10 steps gets me, say, something like 3 orders of magnitude more accuracy in my answer.
If we have to get this to one decimal place, wouldn't it make sense to find a solution to two decimal places and make sure that we're not introducing a rounding error?
Yeah, that's a fair question. So what about rounding errors? Um, if I had plugged in one of these and saw like 0.00001 or something, I might be kind of suspicious, but at that point I might just call that the solution, you know. So the calculator is accurate to something like 9 to 12 decimal places. So none of these were so close that I was worried that we can't tell the difference between a positive or negative output. But that is a fair point. That's actually related to a larger concept in numerical analysis, that what if I had a function that like was really flat? So I'm going to try to draw it here so it looks really flat. Right? Like my ability to tell whether the function is positive or negative for different inputs, it might be pretty hard for me to tell just because of the round off error. And this actually this does cause some issues with stability of some methods and things like that. Uh, I'm trying to pull from my memory that it causes issues with what they call the conditioning of the problem. So this would be an ill-conditioned problem, and it would cause problems like you're mentioning with things like minor round-off errors um, can cause major issues. Or you might say like, I'm going to say I found a solution whenever the output for a given input is close to zero, but like the outputs for inputs that are way far away from the solution are also close to zero for crazy functions like this. So um, yeah, so that is a fair point to consider. In this case, I think we can be pretty confident that the answer is between 1.1 and 1.2, because we were getting numbers like 0.27. Like on the scale of 0.3, is the calculator going to make an error that big? No, so I'm confident it's a positive number. And the same thing with 1.1. I forget what our output exactly was, but it was a reasonably negative number, negative 0.43. So I'm not worried about that. If it came back like negative or negative 10 to the minus 9 or something, I might start questioning whether that's a round off error. But at that point, I would probably just be pretty confident calling that just the solution, an approximate solution.
So I looked at it when I put in 1.15, and that's a negative number. So if I just felt like if 1.15 was negative, 1.2 is positive, to round it to one decimal place, so it might make sense to make it 1.2.
Yeah, so that it's a fair point. It's a question of, when we say one decimal place of accuracy, what do we mean? Do we mean to, within within 0.1 units? Do we mean like give me your best guess? Um, you know, or are we saying find the first decimal point, the first decimal place? Um, yeah, so I mean, we could keep going and keep getting more accuracy. So if we plug in 1.15 and see that that's negative, we know that the solution lives on 1.15 to 1.2. Maybe our best guess now is updated to like 1. 1.175, right? Yeah. um, so maybe we could update our best guess again. Yeah, so we could keep getting more and more accurate. Um, but I think either way that you look at it, we have an interval of width 1 here, or 0.1 here. So our error is going to be at most 0.5. If we guess, a solution of say like 1.15, pick the midpoint, our error is going to be at most 0.05. Getting my decimals all wonky here. And I think we could consider that one decimal place of accuracy, guessing 1.15 is the solution, and we would not be off by more than 0.05 in either direction. Or we could say that the solution is 1.1 something, and our first decimal place has got to be a 0.1 for the solution. Maybe it's 1.13, maybe it's 1.17, but it's 1.1 something.
That makes total sense. I was just thinking about a nonlinear equation that can go to chaotic situations with the error. But as soon as you said, pay attention to the margin of error that you're introducing, and this is a minimal margin of error, that makes total sense.
Yeah, and importantly, this is a nonlinear equation. So this is what we would use something like bisection method, or later on we'll see Newton's method. These are nonlinear equation solvers. So all that we have to be able to do is evaluate the function a whole bunch of times pretty cheaply, like say on a computer, and we can run this method. And we, of course, have to find something to get it started. We have to find an interval where we have that sign change to get it started. So these are nonlinear equation solvers, and Newton's method can be better in some situations, but worse in other situations. Yeah, but the idea of chaos is kind of that that the perfect inputs predict perfect outputs perfectly, but approximate inputs are give poor predictions of approximate outputs. And that that's probably qualitatively related to something like this over here, although I think there might be some nuances between the two definitions of like chaotic systems versus ill-conditioned numerical systems. But I think that's kind of along the right line of thinking, is that there can be problems that, where there are external considerations because we're dealing with approximations here. So that's a fair point. Okay, so any questions on continuity? Any questions on section 2.5? Okay, let's look at 2.6 then, limits at infinity and horizontal asymptotes. Let me switch my share back, make the OneNote a little bigger for you, a little easier to read. Okay, so we talked about obviously regular limits before. We also talked about infinite limits, we called them, where we had like limit x goes to a, f of x equals infinity. We talked about what that means. When we say a limit at infinity, what we mean here is something like this. Limit as x goes to infinity, f of x equals L, a real number. What do we mean by that? Well, kind of qualitatively, this means that the outputs of f can be made as close as we like to the real number L by choosing sufficiently large positive values of x. By choosing my inputs far out to the right on the real line. There's, of course, an analogous definition for negative infinity, where limit x goes to negative infinity, f of x equals L. We just plug in large negative values for x. And we have a similar epsilon delta definition for every epsilon bigger than 0 that constrains the outputs around the limit. There's some real number n. We typically think of this as a big positive number. And we think of it being dependent on epsilon. If I want a smaller corridor around my limit, I probably have to go further out to the right. I probably have to pick bigger inputs, bigger number inputs, such that x bigger than n implies that f of x is within epsilon of L. So it's not only that as we go out to the right, we have to get close to the limit sometimes, right? It's not something like this, where I say, yeah, sometimes I can get close to L as I go to the right, but other times I'm far away. I have to get close to L and stay there. So my function might oscillate around, but it kind of settles down to L like this. And a definition of the term horizontal asymptote, you might have heard of this term before in algebra or pre-calc. if we're looking at a function, f of x, and if it's true that limit x goes to, it should be plus or minus infinity, isn't that? Okay, there we go. Limit x goes to plus or minus infinity, f of x equals L, a real number. Then the line y equals L, we say is a horizontal asymptote of the graph of the function y equals f of x. So this here, this line y equals L would be a horizontal asymptote of this function. So a theorem, if R is a positive real number, so if it's a positive power, then if we look at 1 over x to the R power, limit x goes to infinity is 0, and limit x goes to minus infinity is 0, so long as this is a well-defined thing to ask. If I'm, if R is positive 1/2, I'm taking a square root, doesn't really make sense to say what's the limit as x goes to negative infinity, 1 over root x. The problem is if I try to square root any negative number, the thing kind of blows up. I don't know what to do. So I don't know how I can plug in inputs that get more and more negative when I can't plug in negative numbers at all. So again, so long as this is defined, then the limit at negative infinity is also 0.
Is that n related to the n in the intermediate value theorem?
Oh no, it's
Okay.
kind of related to this, kind of this n up here, but it's just some number.
Right.
So if this doesn't work for some reason for, x's between -1 and 0, but it works for all x's less than -1, then, well, since I'm going towards, since my limit is going to negative infinity, then I can just restrict my domain and say just be below -1. And that's a fine thing to do. And we've done that before with kind of regular limits. We've restricted our domain so we can stick to a piece of the function that's a little nicer. So it's really nothing more than that. Okay, so let's look at a series of limits here and just compute their values if they exist. Let me actually zoom in just a little bit here, make it a little easier for you to see on the screen. I know these limits can sometimes be a little small with all of their little details. Okay, limit x goes to infinity of x squared. So we know what the graph of x squared looks like. It looks like this. And as I plug in bigger and bigger inputs, I get bigger and bigger outputs. We can actually have an infinite limit at infinity. In fact, that's, a fairly common thing to happen. So as I plug in bigger and bigger positive inputs, I get bigger and bigger positive numbers out. Limit x goes to infinity of x squared equals infinity. This is an infinite limit as well as a limit at infinity. And similarly, if I plug in bigger and bigger negative inputs, they turn into bigger and bigger positive outputs. My limit at negative infinity, limit x goes to negative infinity of x squared, is also plus infinity. So the bigger the negative input is, the bigger positive the output is, that limits infinity as well. If I have something like limit x goes to infinity sine of x, it just keeps doing this kind of thing forever. If this interval that I was looking at was, 0 to 2.5 pi or whatever. Here, let's just make it 0 to 3 pi. Or if the interval was 100 to 103 pi, or 1000 pi to 1003 pi, or 1,000,000 pi to 1,000,003 pi, it's going to look exactly the same. No matter how big the positive number that I put in is, it's going to have this same basic shape. And I can see that any limit, for instance, if I thought that maybe the limit was some positive number, go out a little bit, and I'm always going to get a negative output pretty soon afterwards. I'm never going to be able to stay within, say, L over 2 of that limit, because I'm always going to go negative at some point. Or if I thought the limit was 0, I'm always going to have an output of +1 within the next 2 pi units. So I can never stay strictly within an epsilon of, say, even 1, let alone some other smaller epsilon. So we see that this limit does not exist. Something like this, limit x goes to -infinity of 1 over x squared. Well, we might know what 1 over x squared looks like. 1 over x squared looks pretty much like 1 over x, like this, except that negative numbers get squared to positive numbers. So, I mean, the shape is pretty much the same, except that that left-hand side gets flipped up. As I put in larger and larger negative numbers, like -100 squared gives me +10,000, and then I get 1 over 10,000. That's a small positive number. If I put in -1 million, -1 million squared is +10 to the 12th. 1 over 10 to the 12th is a very, very small positive number. This limit is 0. Clearly, I don't have any problems plugging in negative x's into here. I see this as 1 over x to the r, where r is 2, a positive number. And my theorem says this limit's 0. Also, my intuition says the limit's 0. It's usually not a bad idea to get some intuition for what you think the limit is, and then also have some algebraic support for what you think the limit is. Being able to go back and forth between kind of geometric ideas and getting intuition over there versus algebraic structure, very powerful ability to be able to go back and forth between the two. If I look at something like limit x goes to infinity sine x over x squared, now we might be tempted to do something like make this limit x goes to infinity sine x over limit x goes to infinity of x squared, but then I have like a limit that doesn't exist over a limit that's infinity. Like, I really don't know what to do with that. But what I do realize is that sine x is stuck between -1 and 1 on its outputs. So this whole function is stuck between -1 over x squared and +1 over x squared. But these both limit to 0. So essentially, by the squeeze theorem, this limit is just 0. Right? If I think of 1 over x squared looks like this, and -1 over x squared looks like this, as I plug in bigger and bigger positive numbers, I have this kind of sine x function bouncing between the two, but it's getting squeezed closer and closer to 0. So geometrically, I'm comfortable with this result, and algebraically, it makes sense with some of our previous properties and ideas, squeeze theorem, and so on. Okay, limit x goes to -infinity of this rational expression. If I plug in larger and larger negative numbers, what happens to the outputs of this function? Well, I kind of noticed that I get something that's like an infinity over infinity. I get a really big positive or negative number over another really big positive or negative number. This is an indeterminate form, kind of like 0 over 0. When I see an indeterminate form, usually my first thought is, okay, is there some algebraic simplification that I can do to get rid of what's causing this indeterminacy? And here what I'm going to do is I'm going to divide by the biggest power of x that I see, that's x cubed. And I'm going to do that on the top and the bottom. So I multiply by something over itself. Since x is heading toward negative infinity, I can just assume, say, x strictly less than 0. No problem there. I can still plug in large negative numbers. So I don't have to worry about like introducing a division by 0 or anything like that. And I see that this gives me limit x goes to negative infinity by x less than 0. When I multiply through and distribute everything, I get 1 over x cubed minus x squared over x cubed 1 over x, all divided by x cubed over x cubed is 1, plus x over x cubed plus 1 over x squared, and then minus 1 over x cubed. Now my limit laws and properties and so on essentially all work for limits as x goes to negative infinity or positive infinity, with some of these extra little criteria that I'm not like uh that I'm not creating something that's ill-defined or anything like that. So I can make the limit of the quotient of the limits, so long as the denominator doesn't end up being 0. I can make the limit of the sum or difference of the limits, and so on. And then I can apply my theorem up here to evaluate limit x goes to negative infinity of all of these 1 over x to the powers. Or this is what? It's the quotient of, well, limit of 1 is 1, plus limit of 1 over x squared as x goes to minus infinity. That's 0. Minus limit x goes to minus infinity of 1 over x cubed is 0. And in the numerator, I have 0 minus 0 as well. So I didn't end up with a 0 in the denominator, so that 1 there saved the day. If I tried to like multiply by 1 over x to the 4th on the top and bottom, I would have been left with a 1 over x here. Everything would have zeroed out. I got 0 over 0. I'm back to being an indeterminate form again. If I had multiplied and divided by, say, 1 over x squared, I'd have like a 1 up here. And what would I have down here? I'd have well, that would work. I guess it would just be a little more complicated. If I had multiplied and divided by 1 over x, I'd have had an x up here and an x squared down here, and then I'd have still been left with infinity over infinity. So there's kind of a bit of a tightrope that you need to walk here. But this ends up being 0 over 1 or 0. So this limit turns out to be 0. That also meshes with our general understanding of polynomials, that higher degree polynomials grow faster than lower degree ones when large numbers, positive or negative, are put in. So my denominator is getting bigger faster than my numerator because it's cubic versus quadratic. My denominator wins out. Big denominator means small output, meaning an output near 0. If we try to do the same thing here, I have a cubic over a cubic. These are kind of equally matched. If I try to multiply top and bottom by 1 over x cubed, what's going to happen here? Slightly different than what happened above. So distributing my 1 over x cubes, I get a 4 on the top, plus 6 over x, plus 10 over x cubed. And I get a 3 minus 1 over x squared, plus 1 over x cubed. All of these bits go to 0. And I'm left with this 4 divided by 3. Again, I make sure that I didn't create a 0 in the denominator. I didn't do that. So I'm just left with 4 over 3, and that turns out to be the limit. These two polynomials are kind of equally matched. So their ratio tends toward the ratio of their coefficients of their highest degree terms. And then if I have something like this, where the numerator has higher degree than the denominator, I think at this point I have a gut feeling that, okay, the numerator is going to grow faster than the denominator grows. This is probably going to blow up to one of the infinities. So if I try to say divide by, let me try to divide by x squared. Let's try that. In the numerator, I get 3 minus 2 over x squared. In the denominator, I get what? I get 1 over x plus 1 over x squared. And now I have a bit of an issue because both of these go to 0. So this limit kind of like equals, in a rough sense, number over 0. Right? Like if I have 10 candies and I have 0 people to give them to, how many candies can I give to each person? Like kind of infinitely many. So number over 0 is like kind of infinity, but anytime we're dealing with infinities, we have to be really careful about these little details and nuances. What could I do here to make this a little clearer what the answer is? Right, I don't want to go this route. Well, maybe if I divide top and bottom by, say, the biggest power in the denominator instead, just x to the first power, that way I won't zero out the denominator, because that was what caused the problem. Three x squared over x is 3x minus 2 over x divided by 1 plus 1 over x. I know that this is going to go to 0, as is this. I'm plugging in a big negative number. The only place I see an x in either of those terms is in the denominator. Those are going to 0. So this is going to look like limit x goes to minus infinity of 3x. When I plug in a big negative number, I get 3 times big negative number is a really big negative number, or I guess a bigger negative number. This limit is negative infinity. Now, had I had, say, negative 3x squared, etc., if I had gotten a negative 3x here, when I plug in a big negative number, the negative flips it and gives me a big positive output. My output would be positive infinity in that case. So I have to be careful with these infinities, with these infinite limits. Okay, we do have a nice theorem here. We kind of see that these last 3 problems were rational expressions, right? Limits at infinity of rational expressions. And that's what this theorem addresses. If we have 2 polynomials p and q, where polynomial p has highest degree term a n x to the n, and polynomial q has highest degree term b m x to the m, then the limit of their quotient as x goes to either plus or minus infinity is the following. If the degree of p is less than degree of q, if q is the kind of dominant polynomial, if it has the higher degree, it's going to grow faster as I plug in bigger numbers, whether positive or negative, and it's going to drag the whole thing to 0 because the denominator is growing faster than the numerator. Whole thing goes to 0. I've got um, my lowercase and capitals mixed up here. There we go. So if the degree of the numerator is less than degree of the denominator, the limit of the quotient is 0. If the degree of the numerator is bigger than the degree of the denominator, then P is the one that wins out. The numerator gets bigger faster. Our ratio goes to either plus or minus infinity, and we have to do something like this to sort out which of the two it goes to. We just have to be very careful about the sign of the inputs, whether we're going to plus infinity or minus infinity, and the sign of the outputs. Okay. And then we have an over bn, the ratio of the coefficients of their leading terms if the degrees are equal. The way that we had this 4/3 here. Are there any questions on any of this so far? Okay, so let's look at a few last problems. These are problems that, are somewhat related to the stuff that we just talked about, but maybe require a little bit of upfront work. So if I look at this next one, for example, limit x goes to infinity of the numerator, I have square root of 9x to the 6 minus x, and the denominator, I have x cubed plus 1. Now, if I look at this at first glance, I realize this is kind of an infinity over infinity type of indeterminate form. If I'm putting in a big positive number, my numerator gets big positive, my denominator gets big positive. That's like an infinity over infinity, so I'm not sure what happens with this. I guess it could be 0, it could be a number, it could be plus or minus infinity. So indeterminate form. When I see such indeterminate forms, I usually have to do some algebraic manipulation to work out what's going on. Now, what I would love to do with this, I would love to do something like this. Square root of 9x to the 6th minus root x, and get something like, 3x cubed over x cubed plus 1, let's say. And this looks like a rational expression. This looks like what our theorem just said. I would love to do something like this. Now, of course, square roots don't break up addition and subtraction, unfortunately. But I do kind of realize that if x is a very large positive number, the 9x to the 6th dominates the x. If x is even like 1,000, that minus x is minus 1,000 on a scale of like 10 to the 18. It's like nothing, right? So this numerator is basically just like root 9x to the 6th, or it's basically just like 3x cubed. If I had a rational expression that was just limit x goes to infinity of 3x cubed over x cubed plus 1, what would I do? I'd multiply top and bottom by 1 over x cubed. Now, I'm not doing any of this off to the side as kind of like official, work for this problem, but I'm thinking through, what does this kind of feel like? Can I link this new problem that I haven't seen one like this before to an older problem that I've seen one that's like it, right? I'm trying to say, can I place this in the framework of another problem? It kind of feels like a ratio of polynomials. It kind of feels like a rational expression. This is how I handle these types of limits of rational expressions. This gives me an idea. Maybe I could multiply numerator and denominator by 1 over x cubed in this original problem, and it might work. It might not work, right? It might crash and burn, and I have to come up with a different framework or a different idea. But if I try multiplying by 1 over x cubed on the top and bottom, and the denominator works great, 1 plus 1 over x cubed, with no real questions there. And the numerator, 1 over x cubed, well, that's 1 over square root of x to the 6th. But now I have the quotient of square roots. Square root does distribute over multiplication division. So if I have this quotient of radicals that is the root of the quotient. That doesn't work for sums. The root of the sum or difference is not the sum or difference of the roots, but it does work for multiplication division. Right, I can put that inside of there. And I see that my x to the 6 divides out with the x to the 6 there and gives me a 9, then minus 1 over x to the 5th. As long as I haven't introduced any like divisions by 0 or anything like that, I should be fine doing this. I know that my, for instance, square root function is nice and continuous near 9. I know that I can take the limit of the quotient as a quotient of limits, all these kind of things. I can apply all these properties. And I see that ultimately this and this are going to go to 0. And I'm left with square root of 9 over 1 is 3. Exactly as my kind of gut intuition originally led me to suspect. Now, very importantly, sometimes gut intuition leads me to suspect something and it turns out to be wrong. That's why we have to follow it up with careful analysis like this. But, still that helped lead the way. Any questions so far? Okay, so next limit that we want to tackle. Limit x goes to infinity of x minus square root of x squared plus 2x. So a couple thoughts on this one. Again, my always kind of first thing that I think about is like, what if I just plugged in more or less, right? What if I just plugged in infinity? You can't really do that, but what I would get is basically infinity minus infinity. If I think of plugging in a very large positive number, I get very large positive number minus very large positive number. This is another kind of indeterminate form. So like we've seen 0 over 0 several times in the past. We've seen some infinity over infinities. Infinity minus infinity is another indeterminate form. It's like a tug of war. The first infinity wants to pull everything off towards positive infinity. The minus infinity wants to pull everything off towards negative infinity. Maybe in some cases, the first wins or the second wins. Sometimes they tie in the middle. This is another example where it could be really any real number or plus or minus infinity. But we know that with indeterminate forms, the strategy is usually to do some algebraic manipulation and maybe divide out the thing that's kind of causing the problem. Now, I don't see a lot that I can divide out here. I can't really say multiply top and bottom by a certain number because, or by a certain function, because that just gives me some extra messy stuff on the bottom to deal with. Like if I try to multiply top and bottom by 1 over x, then I get an over 1 over x, but then I'm introducing a 0 in the denominator. That's no good. Does anybody have any thoughts on what I could do algebraically with this? I can't split up the radical either.
And you multiply it by like a square root of 1 and then move the root over the other side, so you're squaring that whole thing.
You're really close. We want to multiply by the conjugate. So that was something we saw in the past, but in a different scenario. It's harder to see in this example, but yeah, so great idea. If we multiply by something like the square root of something, but x plus square root of x squared plus 2x. Let's see what happens here. And again, like I've seen multiplying by the conjugate in the past. I see that I have something where I can multiply by the conjugate. Maybe I try this and it just blows up, doesn't work. I have to try something else. So our denominator is just kind of what it is. But one nice thing about our denominator is with the plus sign there, if I plug in large positive number, there's an agreement now in a sense. The first term, x, is going to positive infinity. The second term, root x squared plus 2x, is going to positive infinity. They're being added together now instead of subtracted. Everything is kind of pushing off in that direction. So that's at least a plus. What about my numerator? Well, my firsts give me x squared. My outers give me a plus x root stuff. My inners give me a minus x root stuff, so they go away. That's the whole point of multiplying by the conjugate. And then I get to get rid of the radical minus the square root squared. Don't want to forget that minus on the 2x as well. Let's distribute it through. In the numerator, x squared minus x squared goes away, and I'm left with a negative 2x. Okay. And in the denominator, I just have what I have. Now, it looks like we made it worse. But the big benefit here, well, there's two big benefits. One is I now have a fraction to work with. I have something that looks like a linear over a linear instead of just whatever this goofy thing was that I started with. And second, I, in some sense, kind of have a little more agreement here, roughly speaking, in the denominator. They kind of like both the terms are going towards plus infinity. So maybe one or both of these characteristics that I now have that I didn't have before will be helpful. And in fact, if I think about my previous problem, this really is reminiscent of that because I say for big x's, x squared dominates x. So this radical just looks like square root of x squared. This kind of looks like minus 2x over 2x. And how do we handle, how do we handle rational expressions where the degrees are equal? We divide top and bottom by highest degree and expect to get the ratio of their coefficients out. Let's see if something like that works here. So I see the numerator is a linear, it's x to the first power, and the denominator feels like a linear because the square root of x squared is kind of like an x to the first power, and the x outside is also kind of like an x to the first power. What if I do 1 over x multiplied on top and bottom? So in the numerator, I'm left with just a negative 2. That's probably an improvement. As long as my denominator doesn't blow up, that's definitely an improvement. My 1 over x on the bottom, distributed through to the x, give me just a 1. And put it inside the radical. Maybe I'll do one more step here. I have x squared. Now, keep in mind, 1 over x is 1 over root x squared. So if it comes in the radical, it picks up a power. What doubles the power, I suppose, is how I really ought to say it. But this x squared over x squared is just a 1. And then we have plus 1 over x. This big goes to 0. I'm left with, be a little careful here, 1 plus square root of 1. So I'm left with actually 2 on the bottom. Negative 2 over 2 is negative 1. So this limit should be negative 1. Now, as an aside, if ever you go through the algebra, you calculate your limit, and you say, that was a lot of work, that was a lot of manipulation. I'm not 100% sure that that's right. We can always go back to the empirical definition of a limit, right? So this sometimes doesn't work so great on the calculator plugging in these bigger numbers, but if I look at, say, x minus the square root of x squared plus 2x, and I look at what happens when I plug in bigger and bigger values for x, I'm hoping to see outputs that look like -1. So let me start my table, let's say at 0. And maybe if we increment in increments of 100, fingers crossed, I didn't try this ahead of time, I should have. But yeah, we see outputs that look like -1 for large inputs. This isn't a proof, but this gives me, it gives me a little bit of confidence, or well, a lot more confidence that I didn't make some silly algebra flub somewhere and forget a negative, or mistakenly like the square root of 1, it's easy to just kind of forget about the whole square root and cancel it by accident or something and make a -2/1, right? Just an extra check. The empirical side of things still works. We just have the algebraic side now that we're dealing with most of the time. But if ever I go to a problem like this and I do a lot of work and, you know, I want to check my answer on the calculator or empirically, that's a perfectly fine thing to do. Are there any questions? Anything so far? All right, so I think maybe I'll leave this one problem for next time. We'll make this an exercise. We'll kind of do it just to wrap up this section 2.6, if anybody has any questions on it. And then we'll jump into 2.7 next time. So this will be the first problem we do next time, but try to work through it on your own in the next day or two. And then when we come back, we'll work through this problem, take any questions on 2.6, any questions at that point on 2.6, and then move on to 2.7. So any questions at this point on 2.6 on continuity on anything so far? All right, then I will stop the recording and we'll call it a day.